All right, so today we'll be talking about the motor systems within our car. So it's primarily going to be focused on the motors we use, but the presentation will include just like kind of generally how motors work. And we'll also talk a bit about the motor controllers that we're using and just, yeah. So the agenda, I'm going to start with some electric motor basics. So basically like what we learned in high school about how electric motors work. The two main types of motors being brush versus brushless. I'm going to talk about why you would use one or the other and what parts go into either of them. Also going to be talking about stuff like Hall effect sensors, six-step commutation, sinusoidal control, Clark and part transform, which is useful for understanding electric motors. And then of course, censored versus sensorless motors. And after that, Mike is going to be talking about the Mitsubishi solar car motors that we have, what the motors will let us do, and also the Tritium Wave Sculptor motor controllers that we're buying, or that we already have to actually control the motors. So just to start with the electric motor basics, you guys probably all know this, but just in case, we'll run you through an electromagnet. You basically run a current through a solenoid, so like a coil of wires, and that solenoid will behave like a magnet with north and south poles. So you can see in the diagram, by running the current, you get the magnetic poles. You can also reverse the direction of the current and you'll flip the poles. And so to create a motor, you'll be taking advantage of the fact that you can keep flipping these poles and that having magnets near each other causes an attractive or repulsive force. So then how do you create motion with this? Basically, you use permanent magnets and an electromagnet. And so you see in the top diagram, basically, you just keep switching the current, keep switching the pole of the electromagnet in the middle. And so you constantly have repulsion attraction force in one direction. So basically, if you look at the middle, the south pole will be attracted, the south pole in the middle rotor will be attracted to the north pole on the outer rotor, and also repelled from the south pole on the outer magnet. And so every time it basically reaches its equilibrium, you flip it again. And since it's already in motion, the inertia will carry over and you'll just continuously get this rotating motion. And since field strength changes with the distance of the motors, you can just add more, you can increase the frequency of the magnets. Since field strength changes with the distance from the magnets, you can add more to kind of create a smoother motion. So in motors, you'll see a lot of these coils. And on the top, you see a more conventional brush configuration where the motor is in the middle and the permanent magnets are on the outside. On the bottom, it's the other way around. So you see the coils of wires, and I'll be explaining this farther, but you can see the coil of wires. You just kind of have to choose when to energize the coils to create the poles to cause the attraction and repulsion. So the two types of motors I'll be discussing are brushed and brushless motors for mostly PC. But basically for a brush motor, this is just the simple solution to how you keep switching the current. In its most basic form, you see in the top right, the top right diagram, there's one kind of coil called an armature. And when you run a current through that, you can use the right-hand rule in this diagram to see that basically what happens is you get a really flat magnet where north is pointing up, south is pointing down. And so in this diagram, you'll see since north, on the permanent magnets on the outside, north is on the left side, south is on the right side, the armature will flip so that the upper face currently will point to the right towards south. And when it does this, what happens is that the physical brushes connected to the circuit will move, and it'll rotate, and it'll actually switch the current direction through the armature. And so when that current direction flips, the poles flip, and it'll continuously spin. And I mentioned earlier that you can make this motion a lot smoother by just adding more of them. So you see in the bottom diagram, there's like a lot of brushes, a lot of armatures, and this will create a more smooth rotational movement. So yeah, in the above diagram, basically when the armature rotates 180 degrees, the current will switch. And generally, the brushes are spring-loaded to maintain constant contact. But by doing that, as you might imagine, the spring or the contacts can wear out, they can spark. So brush DC motors were like a very original design, but it's not super useful if you need to be using the motors for an extended period of time. And so the improvement was brushless DC motors. Basically, it's a configuration where you have opposite coils connected as one circuit. And so that's your kind of electromagnet, as you see in the top one. The opposing sides creates one kind of electromagnet, and the permanent magnet is actually the thing that's rotating on the outside. And so by energizing successive coils, you can slowly push the permanent magnet on the outside around. And there's advantages to, so basically when you run it, you energize two coils at once, because since there's multiple coils, you don't only need to work with attracting the permanent magnet with the next coming coil, but you can switch the previous coil to also repel. And so by running two coils at once, this configuration, you generally get more torque, it's more efficient. And so basically it's also a lot more consistent torque. So I mentioned earlier, by increasing the frequency of the armatures and the brushes, you can get more consistent motion. This design is already quite good at getting you consistent torque, so your motion is very smooth. But you need to use Hall effect sensors to track the position of the magnets. So next, I'm going to be talking about kind of what goes into these motors. So I'll be talking about what are Hall effect sensors, how they're
James, can I
used.
jump in here for 1 sec? Just
Right?
one more note on brush versus brushless. The efficiency of brushed motors is typically in the range of 70%, and brushless can get 90% and above. So that's another huge bonus for using brushless motors.
Yeah. So now I'll be talking about kind of censored and sensorless motors and what goes into them, how they kind of measure the position of the motor and how they're controlled. So just a quick refresher on Hall effect sensors. This is used to detect the presence of a magnetic field. So basically you have a thin metal strip in a circuit, and you can imagine when you connect that to a battery, the current kind of just runs through it. But if it's in the presence of a magnetic field, this will cause the electrons to kind of split to one end, and this will create a voltage gradient across the thin metal strip, which you can measure. So you can see in the example, you use a multimeter to measure the two ends of the metal strip. And by having a magnet there, you'll get a measurable voltage based on how close the magnet is, because the magnetic field is affecting the strip. And so the voltage is typically in the microvolts, but you can amplify that with an amplifier. So if you measure the voltage gradient and then run that through an amplifier, you can get a nice measurable voltage to know if there's a magnetic field in the presence. And you can also use a Schmitt trigger after the amplifier if you want to create a digital circuit or a digital signal with the Hall effect sensor. So as you can imagine in the bottom diagram, every time what's the word for the bump? Every time like a tooth comes near, it'll be closer, and then with the Schmitt trigger, you can have that be like a high-low kind of signal. So that'll give you a square wave, and by measuring the frequency of the square wave, you can generally get like the RPM of the wheel. But you can also just use an analog Hall effect sensor to detect position and how close each like tooth is to the Hall effect sensor. As you can imagine, you can use this to get the RPM of your wheel just by measuring the frequency at which your Hall effect sensor is giving you a high signal. And so 6-step commutation is a way we use to control
Basically control the current through the coils in the brushless motors.
Yeah, I forgot to mention something. What did I forget? Oh, I guess it's not in order. Okay, I'll probably end up talking about this later. But if you recall, I'll go back a bit. If you recall this kind of brushless motor configuration, you can see that there are 6 kind of positions or 6 patterns that where you need one Hall effect sensor between each coil, and you'll get 6 different positions for the motor. So by having 3 sensors, you can actually detect 8 patterns, but generally you don't use 2 of the patterns. So you'll see there's 6 patterns here, and the coils are at 120 degrees. So for a complete rotation of 360 degrees, the energizing of your stator coils would change 6 times. So every time the rotor is in an angle between 60 and 120 degrees, you can say a commutation is happening. So for example, a commutation will happen at 60 degrees when your Hall effect sensors detect the rotor position at between 60 and 120 degrees. So we use this for low speeds because generally you use censored motors at low speeds. I think I'll talk about this. Okay, well, basically, censored motors use Hall effect sensor to measure the position of the motor and the speed at which it's turning. So, but that requires sensors, which when you're in situations with like a lot of dust or a lot of vibration might not be ideal. So there's also sensorless motors, which don't include the Hall effect sensors. And they basically measure the RPM of the wheel through back EMF produced by the actual rotor. So if you imagine that you're spinning the rotor not by constantly flipping the current, but just like with your hand, it actually acts as a generator. So when you're running the motor, it creates back EMF that kind of opposes its motion. And you can measure the back EMF to see how fast your wheel is spinning since it's proportional to the speed. But generally the back EMF is very low. And so
Just to note, back EMF is just voltage.
Yeah,
this is generated from the coil.
Yeah, so when the wheel is running at a really low speed, it's a very negligible amount of back EMF, so you can't really measure it reliably. So at low speeds, what we'll do is we'll run using the sensors, so the Hall effect sensors, and we'll be using 6-step commutation to control the wheels. But once we get up to a relatively high RPM and the car is running at a good speed, we can measure the back EMF. And so what this does is it allows us to use or run on sensorless drive modes when we're at high speeds. And this is a lot better than sensor drive modes since 6-step commutation, as you can imagine, is kind of choppy. So by using the sensorless drive mode, it's a lot smoother. And generally how you measure the EMF is you have an ADC that measures it coming out of the motor, and your motor controller will do like the calculations inside. And how it does this, now I'm going to be talking about a very important kind of mathematical thing when it comes to these motors, which is called the Clark and Park transform. Or I think it's the Clark transform and the Park transform are 2 separate things, but when you put them together, it becomes really useful for motors. I think it's generally known as direct quadrature.
Just one more note on the back EMF. Typical like hobbyist brushless motors that you might see on quadcopters or something like that will use the back EMF, but they'll measure the zero crossing point of the phase that's not being driven. So you see the 3 phases here, and there's an earlier diagram where current always flows through 2 phases, and the 3rd phase is not activated. They'll measure the back EMF on that phase, and when it's 0, then that's when they'll commutate and switch the coils that they trigger through. So it's still like 6-step control, but they're just using the back EMF instead of Hall sensors. And the Clark-Park transform isn't used for this type of sensorless control, but it is used when you're using field-oriented control, which is where the sinusoidal drive comes in, that James is going to talk about in a bit. But field-oriented control is, instead of just driving the phases at full speed, just at full current all the time, whenever you're in that range of commutation, then you'll constantly adjust the current based on where it is in that range of commutation, so you get much smoother drive.
Okay, so sinusoidal control, this is used for sensorless drive of the motors, and it's much less choppy compared to the 6-step commutation. And if you can recall, our batteries are DC, but 3-phase sinusoidal control requires 3-phase AC current. And what this basically is that for each of the stator coils, you can imagine, you're powering them kind of out of phase with each other. So the way we create this AC current is we can run pulse width modulation with the MOSFET in varying duty cycles to achieve the sinusoidal current. Since the current through an inductor does not change instantly, so that kind of recreates the sinusoidal power curve that we are looking for. And if you recall from last week, we did a bit on converters, but
so the converter bit, each phase has a half bridge driver on it, where it can drive current either direction through the phase.
Okay, so now for a bit on Clark and Park transform, because it's pretty interesting. I've mentioned multiple times, but electric motors typically run on 3-phase AC power. So again, just imagining that previous example with the stator coils 120 degrees apart, basically you can represent each, you can represent the coil or the motion of the rotor with 3 spatial components, or with 3 components, which we'll call the ABC components. And this is just the 3 AC out of phase currents. And so you can transform this into an orthogonal stationary frame called the alpha beta frame. So if you look in the diagrams, it's the same motion, but instead of using the 3 components, this is just the 2 orthogonal components that you typically use to in math class. And this simplifies the measurement a lot because you don't need 3 components. And so you take the orthogonal stationary alpha beta frame, and what the mathematician, name I forget, thought up of was you basically align the direct axis with the magnetic field axis of the motor as it turns. So now you'll have a rotating orthogonal axis. So basically that bottom sign, or the bottom diagram. And you can see that when you do this, your components, they stop changing. So by matching the rotating reference with the rotation of the rotor, and this is called the rotating DQ reference, you end up with 2 constant components which resemble DC references. And this is much easier to work with because a lot of PID controllers are designed to measure constant references. And what those are like kind of feedback control loops that you want to use to maintain a certain value. For example, if you're trying to maintain a constant temperature within an oven, or in our case, we're trying to control our speed during cruise control, we're trying to maintain a constant speed. And that's where you might see those. But basically, so you started with 3-component rotation, and by converting it into an orthogonal 2-component, and then rotating the reference frame to match the rotation of the rotor, you get you get 2 constant components, which is much easier to work with your motor. And so sensorless versus censored, at low speeds, I mentioned back EMF is really weak. So what we do is that at low speeds, we're using 6-step commutation with our Hall effect sensors. So our motor will be using the 3 Hall effect sensors to kind of detect the speed and position of the motor. But once we get up to a high enough speed, we don't want to rely on the sensors anymore. So at higher speeds, we change our drive mode to sensorless, and it's our motor controller that's compatible with both modes and lets us switch between them. So our motors and motor controllers, basically, we're able to run using Hall effect sensors, but also measuring back EMF. And ideally, we prefer sensorless since it's more of a reliability issue. If our car's vibrating a lot, then our sensors may be inaccurate. But since at low speeds, it's not really doable, we just kind of combine the two to use whenever we best can. So now Micah will be talking about the actual motors that we use. They're called Mitsuba motors, and the ones we have are specifically made for solar car racing so that they fit the like the guidelines. What's the word for guidelines? The regulations and whatnot. But also just they're generally like more efficient for our purposes.
Yeah. So the motors that we have, they're from Mitsuba. We buy them from a company called Nomura, and they make solar car racing products. They're based out of Japan. Yeah, we got them from there. Model number is the M2096D-3, but we also have some custom stuff done to the motors to optimize them for the speeds and currents that we're expecting to be driving them at. So a bit on how we attach them to the motor, attach them to the wheels. They have mounts for direct drive, which is you put the wheel directly on the motor. There's no gears or axles in between, so no extra friction. That means increased efficiency, which we're always chasing. These motors are in the range of 90-95% efficient. So every little bit of efficiency counts. Gears and axles and anything from that will just, then there'd be no point in getting these motors. And pretty much all solar car teams do this. So yeah, we mount them directly to the wheels. We have, as I mentioned, custom wound coils to match the target power consumption of our car. And I'll talk a bit about that in the next couple of slides. So for the dual coil arrangement, when I first saw the motors, I noticed there were six wires coming out of them, which is very unusual for a three-phase brushless motor. So I did some digging and really we should have had better documentation of what we actually ordered. But talking with Robin and Clark, and there's an email thread that went back and forth with Nomura about actually ordering the motors. It all made sense once I found that stuff. So we have two coils in our motors, but it's kind of just one coil, and there's a branch off of the middle of the coil that acts as the tap for the second coil. So the Mitsuba calls this a low speed, high speed coil, or a cruising and overtaking coil. So having the two coils, the reason for that is they can travel at different speeds in different efficiency zones. With the one coil, you're limited to the graphs of the coils are on the right. So you can get up to 612 RPM with one coil, with the other coil up to 720 RPM. Basically, one of them is optimized for high speed, low torque. The other is optimized for lower torque, higher speed. And these values, the exact current consumption and speeds and torque targets were given by the strategy team. Clark worked out a bunch of the math for that. Yeah, we have two coils on the motors, and the ability to switch between them allows us to choose which coil is best for the type of driving that we're going to be doing in a certain day during the competition. So if it's going to be a long day of driving, it's mostly flat, and we expect to be going pretty fast, then we'll go for the higher speed coil. If we're going to be going up and down a lot of hills, and say there might be lots of traffic or something, but the hills is the big part, we'll go for the longer coil, and that will allow us to have more torque. at lower speeds. Well, at any speed, but more torque is the biggest thing that allows us to climb steeper hills and not get stuck. Now, the reason for that difference between the two coils, one of them being long, one of them being short, the longer coil has more inductance. So that's more turns of wire around the center of the electromagnet. And more turns of wire around the electromagnet means that you get a higher electric field, which will translate to more torque as you're rotating the motor around. A higher force, so higher force towards the permanent magnets on the rotor, and that gives you more torque as you're spinning the wheel. And the short coil can run at higher speeds because you're not limited by the back EMF that the coil produces. As the motor is rotating around, the back EMF is always present in the coils. So you just have to drive it at a higher voltage to overcome that back EMF. But when that back EMF becomes equal to the voltage that you're driving the motors at, then you don't get any current through the coil, and that's no extra torque. And that's what's in the graphs on the right. You can see the torque drops down to 0, and you can see the RPM is high when the torque drops down to 0. So that's why that happens. When your back EMF is equal to your driving voltage, then you can't go any faster because you have no more torque. So the short coil gives you more or less back EMF, so you can drive faster before hitting that driving voltage limit of the back EMF. So we can go down to the next page. So yeah, one of the big advantages that Mitsuba sells for these types of coils is you can switch between them, between the high and low speed coils on the fly, just using a switch. So say you're behind a slow car and you want to pass them, be just like a gear shift in a car. You would pull the switch back, switch to your higher speed coils, and then accelerate past the car, and then switch back to your low speed coils to gain higher efficiency as you're traveling at a lower speed. But that can only happen when you're using stick-step control. And the reason for that is with sinusoidal control, the motor controller has to know the inductance of the motors, because that inductance is going to determine the slope of current through the coil during the PWM on time. If you remember the graph that James had there, how the duty cycle of the PWM changed depending on how much current you wanted through the coil. It had a changing PWM duty cycle, and that created your sinusoidal current. Basically, if you have an inductance value that the motor controllers don't know, then it won't be able to control the sinusoidal current accurately. So we won't be able to basically drive the motors at all if you do a switch on the fly while you're in sinusoidal control. So you can do that in six-step control, and Mitsuba sells solar car motor controllers that they use for it. And they only do six-step control, so that's why they're able to do that and advertise that. But with the tritium controllers that do sinusoidal control, which are a lot more efficient, we don't have that luxury. So yeah, that's one thing that we should be careful of, that we don't try and swap on the fly. We always have to remember to reprogram the motor controllers with the new inductance values every time we're swapping coils. So yeah, if we swap them for one day to get higher efficiency on flat ground or more torque on driving up hills, then we always have to make sure to reprogram the motor controllers. So yeah, that brings us to the motor controllers. We're using Tritium Wave Sculptor 22s. All the fancy math that James talked about earlier with the Clark and Park transform. Luckily, we don't have to do that in our own code. We pay Tritium about $6,000 to do it for us. So
Not worth.
Yeah. So these controllers are 9% efficient. Pretty much all the top solar car teams use them. Well, some teams build their own. Delft builds their own, and they win all the time. So I'd like to build their own, but these are really good. and it's crazy amount of research you have to do to know how to build your own properly. Yeah, they're fully configurable through software for your car's system, your target battery voltage, your maximum current, your expected phase currents, and your target speeds, and all that kind of stuff, and all your motor parameters and losses. So the inductance of the motors, that's configurable through software. It communicates over CAN, which is compatible with our system, which is great. Two important distinctions to make that I'm not sure James touched on. There's the rotor RPM, which would be the physical speed of the motor. And that'd be the wheel speed of your road on the ground, of your wheel on the ground. And then there's also the electrical RPM. And that depends on how many pairs of coils there are inside the motor. So if there's only 3 coils inside the motor, then your rotor RPM is also going to be the same as the electrical RPM. But as you start increasing the number of pole pairs in the motor, then your electrical RPM becomes higher than your rotor RPM because your controller is changing the sinusoidal current for every pair of coils that the permanent magnets on the rotor pass. So as you get into higher counts of permanent magnets and coils, then your electrical RPM is going to be a lot faster than your rotor.
Did he cut out for you guys too?
Yeah, I think so.
Okay. Let's just give him a minute.
Yeah, let's give him a minute. Oh, there he goes.
Also the okay, never mind. It might end soon, so just re-click the link if the knowledge share cuts out the Zoom link.
Hello?
Hello, can you hear me now?
Yeah.
My phone just died. All right, so yeah, the electrical RPM is going to be much faster than the rotor RPM at when you get into larger motors and more pole pairs. The other thing to note is that motor controller built into it has a lot of different control loops. It's constantly regulating a couple of different things, making sure that none of the limits are exceeded. One of those is the motor temperature. There's a thermistor inside the motor attached to the coils, and it makes sure that those aren't overheating. It measures the controller temperature, MOSFETs inside there, and it protects those. And then it has software configurable bus current and motor phase current limits. So as the bus current limit, we don't want to accidentally blow the fuse on our battery pack or trigger battery overcurrent events just by running our motors. So we can set a software limit on the bus current and it will regulate that. And the motor phase current, you can also limit that. And that's important because we don't want to burn the cables that we're driving the motors with. Let's go to the next slide, James. So a few important parameters, the motor current and the bus current. It's important to configure those correctly and understand what they mean. So the motor current was the current through the motor coils, and the torque is proportional to the motor current. So you can have a high motor current, and that'll give you a high torque. And the bus current is the current going from the battery pack to the motor controllers. That will be proportional to power. So volts times amps or torque times speed. So the important distinction here is that we can have a high motor current and low bus current when we're driving at low voltages. or not low voltages, at low speeds. So that's important to note that if you have 100 amps going through your motor, if you're not driving very fast, then your bus current is going to be very low. And the one other parameter that's important, somewhat important to understand, I just find cool, saturation current. This goes back into some material properties of inductors and of magnets and materials. Yeah, it's important to know when you're doing sinusoidal control, because in that type of control, the motor controller must always know how much current is going through each coil in the motor to smoothly transition it, and it must be able to control that accurately. What happens in saturation for an inductor? Let's start by what it is. Basically, all your, you probably recognize the graph on the right from a materials class at some point. There's basically a limit of magnetic flux in a certain type of material with certain dimensions that will be equal to all the materials, all the atoms in that material being aligned properly, all the magnetic poles being aligned. That's when you hit saturation. And then you can't hold any more magnetic flux. I know there's a bunch of terms that are mixed up in that explanation, but there's a limit to the amount of magnetic flux that you can have in a certain material. And as we're driving the coils, we're creating magnetic flux inside whatever core material is being used for the electromagnets. So the reason we need to keep track of this is when that saturation point is reached, then the current in the motors starts to get a lot higher. There's a couple graphs of oscilloscopes here. On the left that I found on Stack Exchange,